Hi guys, welcome to another Chemical Engineering Q&A brought to you by the ChemEng Student. In this lesson we're going to take a look at some questions submitted by our students on the topic of non-reactant mass balances. So in this series we're going to look at a different array of topics on questions that you guys, the chemical engineering and also mechanical engineering students, will submit via our website. We do them once a month. This one is on non-reacting systems. We also have one previously submitted for reactor design, which I'll put a link in the description to that Q&A. So the first question was submitted by Mohammed56, and the question involves a distillation column, which is a process unit in which liquid feed mixture is separated by multiple partial vaporizations and condensations. So what we have here is the overhead product is rich in the most volatile component, so that would be A, and the bottom product stream is rich in the least volatile component, so that looks like it's probably going to be C. Now, we need to determine the unknown variables of M3, M5, Y2, Y4 and X4. So just to be clear, the M's in this case are the flow rates of the given stream. So we can see here that M1 is 100 pounds per hour. M4 is 120 pounds per hour. So we need to determine the flow rate of the bottom product and the flow rate of the top product. Now the Y's are and the X's are the fraction within each stream. So for example, Y2, the 2 will denote the stream number. So this is this stream here, so the second feed stream. And then Y2 is going to be the composition of B within that stream. And then likewise Y4 and X4. So it just depends on the stream and the composition of that stream. So the first thing that we'll do is we'll perform an overall balance on the flow rates only. So we know that coming into the system we have M1 plus M2. That must be equal to what comes out of the system, i.e. M3, M4 and M5. So that's where we get this equation here. Now what we can do is we can substitute in the known values that we have, because we know that M1 is 100, we know M2 is 150, we don't know M3, we know M4, which is 120, but we don't know M5. So what we can do is simplify this and get a nice simple expression for M3 plus M5 must equal 130. So therefore, what we can then do here is perform an overall balance on component A. Now the reason I picked component A is because we can mitigate A from M1. We don't have anything in M1. We need to ensure that we can have component A in M3 and M5. Now, component A is the best one to use first because we can see that its composition in M3 is 100%. So therefore, what happens is the only unknown here becomes M5. So we'll take the individual compositions multiplied by their respective streams. So we can see here that component A is in M2, it's in M3, and it's also in M4. It doesn't feature in M5, so we can get rid of that. And what we'll see here is we know the values of M2 and M4. We also know the composition of A in the feed stream, and we also know the composition of A in the middle outlet stream. So if we substitute in these values, and we know that YA3, i.e. here, that's going to be 1 because it's 100% A. The only unknown here is M3. So that works out to be 40.5 pounds per hour. Now that we know M3, we can substitute this back into this equation and determine the value of M5. So M5 becomes 89.5 pounds per hour. So now we have determined the two flow rates that were required at the beginning of the question. So now what we need to do is we need to determine the unknown concentrations. Now there is two ways that we can go about this. So the first way is we're going to take for M2 we're going to look at the composition makeup because we have a two component mixture here. So we know that 35% is brought in by A, so therefore if we do 1 minus the composition of A, that will give us the composition of B. So therefore we know that the concentration of B in the second inlet stream is 65%. So that's how we would go about working out the individual stream concentration for what you would technically class as a binary stream, because we only have 2 compounds, whereas here we have 3 compounds. So we have to do a bit of manipulation in order to achieve the values of X4 and Y4. But what we'll do now is we'll perform an overall balance on component C, and you'll see why we'll do this in just a second. So again, we have C featuring in M1, we have C featuring in M4 and in M5. Now we know the composition in M5 and we know it in M1, but we don't know it in M4. So that is one of the things that we need to determine. So now we can manipulate this equation because the only unknown here is XC4, i.e. X4 here. So when we solve this equation and we rearrange, we work out that X4, so the composition of C in stream 4 is 0.36, i.e. 36%. Now that we know that, we can then say that the compositions of A, B and C must equal 100%, i.e. 1. We know that A brings 0.1, we know now that C brings 0.36, so therefore we can work out that YB in stream 4 is 54%. And that's how you would go about dissecting a problem like this. So in order just to summarise everything that's asked, we now know the compositions of the Y2, X4 and Y4, and we know the flow rates of the stream 3 and stream 5. So again, that's quite a good introductory question. It should be fairly straightforward, but if you struggle to start a question, it can often be a bit overwhelming. But that's how you would go about dissecting a question like that. Now, question number 2 was submitted by Steph46, and she asks, can you solve this question here? Now, we don't have a diagram this time, so what we'll need to do is we might need to construct a block diagram. But we'll have a read at the question first, and it says that an aqueous solution of sodium hydroxide contains 20% sodium hydroxide by mass, and it's desired to produce a product with 8% sodium hydroxide by mass. Now, it's desired to achieve this through the dilution using water, a water stream, and we need to determine the following ratios, i.e. the kilogram product of solution per kilogram feed of the solution, and the litres of water per kilogram of feed solution. Now, this can seem a bit overwhelming to start with, but if we can create a block diagram from this information, it should make a visualization a bit easier. So I always recommend with these types of questions is try and construct a block diagram first. So we'll start off with our block. This would be our dilution tank. So what we say is that we know that we have 0.2% or by mass, so 0.2 kilograms sodium hydroxide. So therefore we know that the other composition, because it's an aqueous solution, must be 80% water. Now what we'll do is because we don't have an actual mass here, we're going to assume a basis of 100 kilograms. Now you can pick a basis of anything that you want, but usually 100 is the standard to use because that's how you would be able to convert your percentages into whole numbers. So we now know what's coming into the system in terms of the feed. We don't know what's coming in terms of the water, i.e. we don't know the flow rate and we don't know the mass. However, what we do know is that in the outlet stream, we only have 8% sodium hydroxide by mass, i.e. 0.08 kilograms. And that means that the makeup to make it to 100% must be 92% water. Now again, we don't know the flow rate of this system, but we should say that we have enough information to be able to work out M2, M1 and V1, because we will need them in order to satisfy part A and part B. So the first thing we're going to do, again, is I always advise do an overall balance. Even if you can't solve it, just perform an overall balance, and that will let us see what type or degree of freedom we actually have. So overall, we can see that we have 100 coming into the system, so 100 kilograms coming in, plus M1, so that's the amount of pure water coming into the system that we're going to use to dilute it, and that must be equal to M2. So that should be fairly straightforward. Now, we know the information about the sodium hydroxide. We know more about that than we do the water, because we don't know how much water is actually coming into the system. But what we do know is that there is no sodium hydroxide in this stream. So therefore we can mitigate that and work out the value of M2 based on the sodium hydroxide balance. So when we rearrange this, we can see that the flow rate of M2, i.e. the product stream, is 250 kilograms. Now that should be very simple in order to deduce now the value of M1, because we just rearrange the overall balance and we know therefore the M1, the amount of pure water in the system, has to be 150 kilograms. Because we'd have 100 coming here, then 150 would give us our 250. So that should be fairly straightforward. Now the ratio of the kilograms of product per kilograms of feed. We can now determine this because we have M2 and we have M1. So we just do 250 divided by 100. That will give us a ratio of 2.5. Now part B now wants us to determine the ratio between the product and the amount of water, the amount of water and the feed coming into the system. So the first thing that we need to do here is work out the volume of water within the system. Now we can do that by working out the mass. We know now M1 is pure water. So we know that the mass of the water, and if we divide that by the density of the water, that will give us our volume. Because if our mass, we'll do a unit balance just to make sure this works. We know that the mass is in kilograms, and we know that the units for density is kilograms per meter cubed. So when we divide these, the kilograms will cancel and the meters cubed will shoot up to the top of the fraction. And therefore our units become meters cubed, and that's your volume. So when we do this, we can see that our volume becomes 150 litres, i.e. I just use meters cubed, but again you can use litres, it just depends. So here we're working in litres, so it will be 150 kilograms divided by 1 kilogram per litre, i.e. we have 150 litres of water coming into the system. Now that means that a ratio for the litres of water per kilogram of the feed can now be found, because we now know that we have 150 litres coming in divided by 100 kilograms of feed would give us a ratio of 1.5. And that is as difficult as that question gets. I think probably the hardest part is deducing this diagram, because once you can construct your block diagram, it's very easy to visualise what's going on. So again, care must be taken when you are reading the question just to try and deduce some sort of block diagram, and that should help you on your way. Now question number 3 was submitted by Amara, and it gives us a mixture of sulfuric acid, which is 60%, with nitric acid 20%, and water, which is blended with half of its own weight of a mixture containing equal parts of all 3 components. And we need to determine the composition of the resultant product. So I think the part that is causing the problem here is probably from this point to this point. That's probably the bit that's causing the problems. But again, let's see how we can deduce a block diagram from this. So we can start off with the first feed coming in, because we know that this is going to be 60% sulfuric acid, 20% nitric acid, and then the rest is got to be made up of the water, so therefore 20%. So that should be easy enough. Now what we'll do here is, because we talk about the half, so we know that this feed coming in here would be a half. So therefore, if we scale this up, because the fractions can often make it a bit difficult, then if we scale this up and make this 1, then that means that this stream must be double this stream, i.e. this would be half of that one. So this one is obviously going to be double this stream here. So if we make this 2F, what that means is we can make this F. Now that means that this stream is a third of each component. So 33.33% of each component is made up of this stream here. And we can deduce this as F. Now this should hopefully give us enough information to be able to solve and determine the composition of the resultant products. Because we now know that F, so F coming in here plus 2F, means that our outlet stream must now be 3F. So what we can then start to do here is balance the individual components. Now again, you can pick any component that you want. Here I've chose sulfuric acid to do it first. Likewise, you could choose the nitric acid, or you could even try the water. The principle is still the same. So what we'll do is, we know that we have 0.6%, or sorry, 60%, so that'd be 0.6, if we assume the basis of 100, would multiply by 2F plus a third, because remember each component is a third, so it doesn't matter which one of these we use, this value will always be a third. So that'll be a third multiplied by F is equal to X1, that's the composition of the sulfuric acid in the outlet stream, so that's multiplied by 3F. So what we'll do is we'll start to multiply this out, and then we can start to simplify the system, because what we now have here is that all the F's cancel each other out, because we can now see that 0.6 times 2F would give us 1.2F. A third of F is just going to stay there, and then we have 3x1F. Now the flow rates, we can assume under steady state conditions that F must be equal at each part. So therefore the F's will cancel, and now we can rearrange for the only unknown within the system to be x1. So that means that x1 is now 0.51, i.e. 51% of the product stream is made up of sulfuric acid. Now we can do the exact same methodology for the other components. So we'll do the same thing for the nitric acid. We'll do our 0.2 this time, multiplied by 2F, a third F, because again these are equal parts, so it's a third, equals x2 multiplied by 3F. We do exactly the same thing. We can see that these F's will cancel, so we get an x2 value, sorry that should be x2, we get an x2 value of 0.24. i.e. 24% of the product stream is made up by nitric acid. Now we could do the same thing for the water balance, but what we now can say is we know the composition of 2 of 3 of the products. So we now can just work out a nice simple equation. We know that each composition must add up to 100%, i.e. 1 in decimal form. So we know that x1 and x2, so we can rearrange this in order to find x3. So x3, the composition of the water, is going to be 0.24, i.e. 24% of the product stream is water. And that's how you would go about solving that kind of question there. The trick here lies in the nomenclature as to how you begin to solve your block diagram. So the theme that you should see in this is that when you solve these kind of problems, the key thing, as I'll say again, is always to do with the block diagram. If you get your nomenclature right, it can make your life a hell of a lot easier when you come to actually solve these questions. So we know, just a summary, that the sulfuric acid is 0.51, i.e. 51% sulfuric acid, 24% nitric acid, and 24% water. So that's the end of this lesson. Thanks for watching. The next Q&A will be on the convective heat transfer. So if you want to submit your questions, please visit us at www.chemengstudent.com. I'll put a link in the description to the website. Please feel free to email us directly or through our contact us page with your questions and any other details that you feel are relevant to convective heat transfer. Thank you for your time. If you like this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. And we hope to see you in another video.